life on other planets, the quest for biosignatures and exoplanets. Billions of stars, countless planets. Are we alone in the universe? Get ready to discover how humanity is searching for the answer to this fundamental question, reaching into the farthest corners of space. Since time immemorial, humanity has gazed at the night sky, pondering one of the most profound and captivating questions. Is there anyone else out there? Are we alone in this vast and amazing universe? This idea has permeated myths, inspired philosophers, and captivated the minds of scientists for millennia. From the ancient Greeks, who imagined infinite worlds, to Giordano Bruno, burned at the stake for believing in countless stars with their own inhabitants, the concept of extraterrestrial life has always been with us. Today, this question is no longer just the stuff of fantasy or religious dogma. It's become the central focus of an entire field of modern science. Astrobiology. We're not just guessing anymore. We're searching. We're searching with the most powerful telescopes, sophisticated algorithms, and daring ideas. Our quest isn't simply about finding little green men, as often portrayed in pop culture. It's a fundamental investigation that could revolutionize our understanding of life, its origins, and its place in the universe. Imagine, every night, a canvas of hundreds of billions of galaxies stretches above us, each containing hundreds of billions of stars. And each of those stars could very well have its own planets. Even if the probability of life arising on one particular planet is minuscule, the scale of the universe is so immense that a simple multiplication of these numbers suggests there has to be something else out there. This section is just the first step in our fascinating journey. We'll begin by grasping the magnitude of this mystery and understanding why this question is so important to us. After all, the answer won't just satisfy our curiosity. It could change our self-perception, our place in the cosmos, and our understanding of what it means to be alive. We're moving from philosophical musings to the concrete scientific steps humanity is taking to find the answer. We'll learn how scientists approach this grand challenge, what tools they use, and what discoveries have already been made, bringing us closer to solving this great mystery. Did you know how astronomers discover planets beyond our solar system that are impossible to see with an ordinary telescope? Once we grasp the enormity of the question of extraterrestrial life, the next question arises. How do we even search for something so far away? We can't simply grab a telescope and see planets orbiting other stars. They're too small and dim compared to their dazzling stars. This is where exoplanets, planets outside our solar system, and the amazing methods of their detection come into play. An exoplanet is essentially any world that doesn't orbit our sun. For a long time, their existence was just a hypothesis, but thanks to technological advancements, especially over the last 3 decades, we've discovered thousands of these worlds. But how? One of the most successful ways is the so-called transit method. Imagine a tiny fly passing in front of a bright light bulb. For a moment, the light dims slightly. Similarly, when an exoplanet passes in front of its star from our point of view, it blocks a small portion of its light. Telescopes, such as the now-retired Kepler and its successor TESS, constantly observe thousands of stars, looking for these tiny, periodic dips in brightness. Each of these blinks can indicate the presence of a planet. Another important method is the radial velocity method, or Doppler spectroscopy. It's based on the fact that a planet orbiting a star causes the star to wobble slightly, due to its gravitational pull. This wobble, though microscopic, affects the star's light. When the star moves towards us, its light shifts towards the blue end of the spectrum. When it moves away, it shifts towards the red. By measuring these Doppler shifts, scientists can determine the presence of a planet and even estimate its mass. It's like listening to a star sway under the influence of an invisible companion. Thanks to these methods, as well as other less common ones, such as direct imaging, when a planet is photographed directly, which is very difficult, and gravitational microlensing, we've already discovered over 5,000 exoplanets. Among them are gas giants similar to Jupiter, but orbiting very close to their stars, hot Jupiters, and super-Earths, planets larger than Earth, but smaller than Neptune. Some of them are located in the so-called habitable zones, which we'll talk about next. These discoveries don't just add to a catalog, they change our understanding of the diversity of worlds and the conditions in which life can exist. Ever wondered why the perfect balance of conditions is needed for life to arise on a planet, turning it into a cosmic Goldilocks? So we know how to find exoplanets. But out of the thousands of discovered worlds, which ones could be home to life? This is where the concept of the habitable zone comes into play, or, as it's also known, the Goldilocks Zone. It's not just a poetic name, it's a very accurate description. Remember the story of Goldilocks and the Three Bears? The porridge has to be not too hot and not too cold, but just right. It's the same with planets. For life as we know it, liquid water is critical. Water is a universal solvent, a medium for chemical reactions, a transport system for nutrients and waste. Without liquid water, at least on the surface, the emergence and maintenance of life seems highly unlikely. And for water to remain liquid, a certain temperature is needed. If a planet is too close to its star, the water will evaporate, turning into steam. If it's too far away, it will freeze into ice. The habitable zone is precisely that region around a star, where the temperature on the planet's surface allows water to exist in a liquid state. This zone isn't fixed. Its boundaries depend on the size and brightness of the star. Hot, massive stars have wide and distant habitable zones because they emit a lot of heat. Dim, small red dwarfs, on the other hand, have very narrow zones located close to them. It's important to understand that finding a planet in the habitable zone is only the first, albeit very important, step. It's a necessary but not sufficient condition for the emergence of life. A planet may be in the right zone, but not have a dense atmosphere that would retain heat and protect it from deadly radiation. Or it could be a gas giant without a solid surface. Or its orbit could be too eccentric, leading to unbearable temperature fluctuations. However, the search for planets in these Goldilocks zones is a priority for astrobiologists. When we discover such a planet, it immediately becomes the #1 candidate for further, more detailed study. We begin to dream that there, perhaps, lie hidden oceans, clouds, and who knows, even simple or complex forms of life. This anticipation is one of the most exciting aspects of our search. Each time we find a new world in the habitable zone, we take another step towards answering the question of whether we are alone. It's not just numbers and formulas, it's hope and inspiration, driving science forward and bringing us closer to the greatest discovery. What if, by looking at a distant planet, we could smell its atmosphere and sense the scent of life? That's exactly what astrobiologists are trying to do. looking for the invisible fingerprints that living organisms leave in the chemical composition of other worlds. We've learned how to find planets that are in the right places, in habitable zones. But how do we know if life has actually arisen and is thriving on these distant worlds? This is the question that makes us look not for the organisms themselves, but for their fingerprints, the so-called biosignatures. These are chemical compounds or other signs that are highly likely to be produced only by living beings. The most powerful and perhaps the most discussed marker is oxygen. On our Earth, its abundance in the atmosphere is a direct result of photosynthesis, a process carried out by plants and cyanobacteria. Without life, free oxygen would quickly enter into chemical reactions with rocks and other gases. Therefore, the detection of a significant amount of oxygen on an exoplanet, especially in combination with gases such as methane, would be incredibly strong evidence. Why methane? Because on Earth, most of the methane is also of biological origin, for example, from microorganisms, and its coexistence with oxygen in the atmosphere in an out-of-equilibrium state, that is, they would quickly react with each other and disappear if there were no constant replenishment, is a convincing sign of an active biosphere. Water, although not a biosignature in itself, remains a fundamental element. Its presence in liquid form is a prerequisite, and its vapors in the atmosphere may indicate potential water reservoirs on the surface. In addition, scientists are looking for other potential biosignatures, such as ozone, which is formed from oxygen, ammonia, hydrogen sulfide, and sometimes even more complex organic molecules. The key idea isn't to search for one specific gas, but to detect an unusual chemical cocktail in the atmosphere that is difficult to explain without the involvement of biological processes. How can we see this? The main tool is spectroscopy. When light from a star passes through the atmosphere of an exoplanet, various molecules absorb it at certain wavelengths, creating a unique fingerprint in the spectrum of light. Modern space telescopes, such as the famous James Webb, JWST, have an unprecedented ability to analyze this light, allowing us to peer into the chemical composition of the atmospheres of distant worlds and look for these subtle but vital traces. However, this search is full of challenges. There are false positives, non-biological processes that can mimic biosignatures. For example, volcanic activity can release methane, and some photochemical reactions can produce oxygen without the involvement of life. Therefore, it's crucial to be careful, to look for several independent signs, and to understand the geological and physical history of the planet in order to rule out non-biological explanations. It's a complex but incredibly important detective work that brings us closer to solving the greatest mystery. Did you know that to search for life on planets hundreds of light years away, humanity is building telescopes worth billions of dollars, capable of detecting changes in the brightness of a star by just 0.01%? We've already talked about how the search for exoplanets and biosignatures is an extremely difficult task. It's like trying to spot a grain of sand on a beach while being on another planet, and then determining its chemical composition. But humanity doesn't give up. Our main detectives in this cosmic investigation are the most powerful telescopes and ambitious space missions. Let's start with those who have already revolutionized the field. The Kepler Space Telescope, although it has completed its main mission, was a true pioneer. It closely monitored a small area of the sky, discovering thousands of exoplanets using the transit method. Its data is still being analyzed, and new discoveries continue to emerge. It was followed by TESS, Transiting Exoplanet Survey Satellite, which scans almost the entire sky, focusing on the nearest and brightest stars, making the planets it discovers excellent candidates for further study. But the real game-changer for the search for biosignatures has been the James Webb Space Telescope, JWST. Launched in late 2021, this instrument is a marvel of engineering, equipped with a huge mirror and hypersensitive infrared instruments. Unlike Hubble, which predominantly sees invisible and ultraviolet light, JWST specializes in the infrared range. This is critical because it's in infrared light that the chemical fingerprints of molecules in the atmospheres of exoplanets are best read. Imagine trying to hear a whisper in a noisy room. JWST is a highly sensitive microphone capable of picking up that whisper at enormous distances, even through cosmic dust. It has already begun to provide unprecedented data on the composition of the atmospheres of some exoplanets. The future also promises new breakthroughs. Concepts for next-generation telescopes are being developed, such as the Habitable Exoplanet Observatory, Hadex, and the Large Ultraviolet Optical Infrared Surveyor, Luvore. These giants will be even more powerful, capable not only of analyzing atmospheres, but also, perhaps, of directly photographing some exoplanets, blocking light from their stars with special star shields, coronagraphs. These telescopes are our eyes and ears in space. They allow us not only to see distant worlds, but also to breathe their atmosphere, to feel their temperature. Each new generation of telescopes brings us closer to the moment when we can confidently say, yes, here perhaps there is life. This is a colossal investment in technology and knowledge, but the stakes are incredibly high. The answer to a question that has intrigued us since the beginning of time. What if the most amazing discovery about extraterrestrial life awaits us not in distant galaxies, but right here, on the doorstep of our cosmic home, hidden under the ice or in the dusty craters of our nearest neighbors? So far, we've been talking about searching for life on distant exoplanets. It's exciting, but incredibly complex. What if the most important discoveries await us much closer, right here in our own solar system? Some of our nearest neighbors, although without obvious surface life, hide conditions under their shells that are quite suitable for microorganisms. These aren't just hypotheses. These are places where we are already sending spacecraft for direct study. Let's start with Mars, the red planet. Once upon a time, Mars was warm and wet, with rivers and possibly oceans. Evidence of water in the past, dried up riverbeds, minerals that form only in the presence of water, and polar ice caps. Today, Mars is a cold, dry desert, but the water hasn't gone anywhere. It's locked under the surface in the form of ice or brines. Rovers such as Curiosity and Perseverance are actively searching for traces of ancient life, analyzing rock samples. And periodic detections of methane in the atmosphere, although controversial, raise questions. Is it not a product of the vital activity of underground microbes? Let's move on to the gas giants and their moons. One of the most intriguing targets is Europa, one of Jupiter's largest moons. Under its thick, icy shell lies a vast ocean of liquid water, twice the volume of all Earth's oceans. This ocean is heated by the tidal forces of Jupiter, creating internal heat. Scientists believe that hydrothermal vents may exist at the bottom of this ocean, similar to those that support unique ecosystems in the Earth's ocean depths. The Europa Clipper mission, scheduled to launch in the coming years, will study Europa, trying to confirm the presence and composition of the ocean, as well as to find potential biosignatures. Another favorite is Enceladus, a tiny moon of Saturn. Images from the Cassini mission showed that Enceladus ejects huge geysers into space, consisting of water vapor and ice particles. Analysis of these emissions revealed not only water, but also organic molecules, as well as silicon particles, indicating hydrothermal activity on the bottom of its subsurface ocean. This means that Enceladus has all three key ingredients for life: liquid water, a source of energy, hydrothermal vents, and organic substances. These worlds aren't just cosmic objects, they're potential cradles of life. Studying them gives us a unique chance not only to find extraterrestrial life, but also to understand what it might look like in conditions different from Earth. Perhaps the answer to the question, "Are we alone?" will begin with our nearest neighbors. We are actively searching, but the universe responds only with deafening silence. What lies behind this cosmic silence? The absence of other civilizations, or something much deeper and more alarming? We've come a long way exploring distant exoplanets and potentially habitable worlds in our solar system. We are building increasingly advanced tools to peer into the most hidden corners of space. But despite all our efforts and the billions of stars that would seem to be teeming with life, the universe still maintains a deafening silence. This phenomenon is known as the Fermi Paradox, named after physicist Enrico Fermi, who once asked, "Where is everybody?" The Fermi Paradox presents us with a profound mystery. If life is widespread and intelligent civilizations inevitably develop, why haven't we detected any traces of them? There are many hypotheses. One is the rare Earth hypothesis, suggesting that the conditions for complex life are unique. Another, the Great Filter, states that there is a critical barrier on the path of life's development to intelligent civilization. This filter could have been in the past. The emergence of life is incredibly complex. Or await us in the future, self-destruction of civilizations. Perhaps all highly developed civilizations reach a point after which they disappear. There are also less pessimistic explanations. Perhaps we are simply looking in the wrong places. Our SETI, Search for Extraterrestrial Intelligence, search has only covered a tiny portion of the sky. Perhaps they use other methods of communication or deliberately avoid contact. The zoo hypothesis, or cosmic distances, are vast, and the lifespan of civilizations is so short that we simply haven't crossed paths. Nevertheless, the future of astrobiology is incredibly promising. With each year, telescopes are becoming more powerful and detection methods more precise. JWST is just beginning to characterize the atmospheres of exoplanets, and its successors will be even more advanced. Missions to the oceanic worlds of the solar system, such as Europa and Enceladus, may bring direct evidence of microbial life in the coming decades. We will also continue to improve SETI methods, perhaps moving to the search for technosignatures, traces of large-scale engineering. No matter what we find, microbes on Enceladus, biosignatures on a distant exoplanet, or the continuation of the Great Silence, each step in this search expands our understanding of the universe and our place in it. This journey is not only about finding others, but also about deep self-discovery. And this is just the beginning. Hopefully, this journey through the vast expanses of the universe and the search for answers to eternal questions has inspired you as much as it has inspired us. If you want to continue exploring the mysteries of space, learn about the latest discoveries in astrobiology, and stay up to date on the most exciting scientific achievements, subscribe to the Epoch Echoes channel and like this video. Your support helps us continue the search.